So today we are going to start with a very important and interesting application area, and this happens to be from one of the recent product translations which we have done across, and that's available now. The area essentially is what is called a super resolution microscopy. Now, because I'm not assuming that all of you have some background or some already pre-existing awareness about what super resolution or what microscopy as such means, or even I'm not assuming that you are very clear about the thing called as resolution. So what I would be doing is I will be starting with essentially going to the basics of how microscopy imaging works and what is this concept of resolution, from where does it origin. And once we know exactly what is the point of origin of the concept of resolution, then we will enter into defining what is super resolution. So that's what I would be covering today. And how we have been able to do this super resolution has essentially been through adversarial learning, and that's the key crux of the takeaway message for today's class. And then all the things which you have learned till now in terms of adversarial learning and perception loss, so we are not getting into details of how exactly it's implemented. And the reason for that is you're already aware of how it's implemented. So what we are going to essentially do now is we will be actually working out on exactly how this will be used in this particular application area. So let's begin with that. Now, traditional microscopy, if you know about it, then so how many of you are aware about traditional microscopy things? You can write in the chat as such if you wish to tell me. How many of you are aware of what is traditional microscopy? There are a lot of people who are joining. Okay, so I would assume that nobody really knows about it, and then let's start. But please tell me a yes or a no or something on the chat box by typing it over there. Otherwise, I clearly don't get to understand whether you are able to comprehend, or even whether the audio, video, and things are coming across to you properly or not. Okay. Now the point is, in case of traditional microscopy, what happens is what you see over here is traditionally what is called as a pathological lab. Now, even for the current crisis situation of COVID-19 working out, now here also you would be seeing that there is a similar kind of a pathology lab where things get tested. The only difference is that microscopes are not typically used. There is a different kind of a biochemical process called as a polymerase chain reaction, which is used in order to confirm COVID-19 and whether you are infected with that or not. So the coronavirus will have a certain kind of a RNA strand, and that particular RNA strand is going to release out a certain kind of proteins and UC. But other than that, say you have malaria or you have typhoid or any, and if you want to just look into your blood test, other than blood grouping, then how you would be doing is that over here there would be this person who is called as a pathologist. So he is typically a doctor who has expertise in understanding of how cellular behaviors work. And this person over here is who is called as a medical lab technologist. So this is the person who prepares the glass slides and gives it to this person over here who is the doctor to look under this device, which is called as a microscope. Now, this device typically gets its name as a microscope from the fact that it can allow you to look into micron-sized things in a very standard visible. So in your naked eye, the smallest of a thing which you can see is in the order of, say, sub-millimeters. So 1 millimeter is what you typically see on the scale. And if you are going very close by, then maybe less than a millimeter is what you can see, half a millimeter or 0.5, 0.7. So the lines which we draw typically with our ballpoint pens while writing. Ballpoint pens have a thickness of about 0.7 millimeters. So 0.7, 0.5 or very thin ones have 0.3 millimeters or something of that sort. Now, somewhere about 0.1 millimeter is where we cease to see, or if you have lines which are finer than 0.1 millimeter and located one beside the other, then you typically cannot make a distinction between them with your naked eyes. So now, and then that has a lot of these beautiful things. So Apple comes up with these displays which are called as retina display, and they call it as retina display because it gives you an image which is very seamless and smooth to your retina. For other ones, you will still be able to, if you go very close to the screen, then you would be able to see those pixels over there. Now, the whole point over here is essentially on a term which is called as resolution, and resolution is basically what is the smallest possible distance between two neighboring lines which you can discriminate. If you are not able to discriminate between the two lines, then there is no resolvability available for you. Okay. So as we go over here, we'll get into how that thing works. Now what our task over here was basically that this guy wants to look at something at micron levels. So basically, say your lines are closer to each other at a spacing of 1 micron or 2 micron, and now he wants to discriminate between them. So the only way you can do is using your fundamentals of optics of lenses. So let's get into that one. So now, before that, the point is like, what is this whole process which is used over here? Now, that particular science is what is called as histopathology. Now, histopathology is known as the science of study of tissue. So, histo is tissue and pathology is some sort of a disease. And essentially, histopathology means that the study of disease in soft tissues of the human body. And soft tissues or tissues as such are what make up your body. So there are cells, there are conglomeration of cells along with some things which are outside the cell and inorganic or non-living in nature is what is called as an extracellular component. They can be matrices, they can be fluids, it can be water, all of these kind of things, water, fat, etc., etc. And that together makes up your tissue. And tissue gets together to make up an organ makes up a system, and then a set of systems makes up the human body or the organism over here. So we'll get into the study of tissues as such. Once you get into cells, then it's in a submicron level, but more or less the study of tissues and cells together is what is called as a histopathology. So the idea is that if I want to study the tissue composition at a particular location, which I give as in over here. So what you see is essentially a heart, and there is a part of the blood vessel around the heart which is taken over here. And now what my job is essentially to see what is the composition of the tissues in that blood vessel over there. So what I'm going to do is I'm first going to take out a part of that tissue, and then this is through a process which is called as biopsy. Now, once I take up that part of the tissue through this process of biopsy, then the tissue is a very soft structure. I mean, your hand or anything, you press it down, it's very soft. If you try to cut it down, typically it's too hard. I mean, too difficult to cut. So you need a very sharp blade and you need a very pinpointed action, and then only you will be able to cut. But then also, there is no guarantee that you will get down a very thin slice and a very straight cut over there. So the reason for doing this is if I have this thick, say I took your whole finger and I want to look into tissues of the finger, I will not be able to see. I will have to make it into thin slices or cut it somewhere open so that I can open it up and inside I can see that. So for that purpose, you need to cut open this structure. And in order to cut open this structure, what you do is that if it is very soft, then it's hard to cut it down. So we make a process which is called as fixation of the tissue. So what you do essentially is you pull out all the fats by doing some sort of a chemical processing, and then also pull out all the water. So you dissolve all the fat in some sort of fat soluble chemicals like formalin, and then you dissolve and then you extract all the water by doing a drying process, and that is by basically dipping it in alcohol. So alcohol is a drying agent. It absorbs a lot of water and then it dries out the tissue, and now it starts to become hard. But then the moment it becomes hard, and because everything was pulled out over there, it also loses its tensile strength. So now it will become very crumbly and it breaks apart. So what you do is that at that point of time, while you are doing all of this process, you take this one very delicately and put it inside wax, and then standard beeswax or paraffin wax or whatsoever. And then in that, generally we prefer paraffin wax because when it cools down and hardens, then it becomes very hard. So you have seen candles, how hard they are typically when it's cooled down. It's not in a molten state. So if you put anything inside the candle, say imagine that wick of a candle, the cotton thing which is present in the middle of a candle. Now that is typically soft, but because that is kept inside the candle and it's dipped in and covered in wax. So if you light a candle and then you basically blow it off, then you would see that after it cools down, the wick of the candle also becomes pretty hard. It does not remain soft, and that's because that wax which goes inside has made it hard. So what we do is we do the same thing for a tissue, and that fills up these empty spaces inside the tissue over there and makes it hard. Now that it has hardened up, this really solves a lot of our problems for now. So this whole thing, you can take it up and so you can take all of these things and essentially now you can slice them down completely. Okay, so just so now what will happen is, now that you are able to slice it up, so this slicing essentially means that you will be basically breaking it down and getting down thin paper-like sections over there. And then in these paper-like sections are what are things of importance to us. So now what will happen is that now that I get these paper-like sections coming over here, so I'm going to take each of them and put it on a glass slide. So that is this next process which happens over here. You put it on a glass slide and then you stain it using some colors. And what these colors are supposed to do is they will give down a different kind of a cell or a tissue, a different kind of a color. And then you put it under a microscope. You have light coming down from the bottom part over here, and then you can see through these lenses. And then you get down an image which looks like this. So here, if something is, you would be able to see some strains of blue, some strains of red, and some things which accumulate together in blue and red and become like purple. And then each of them has affinity to belong to a different kind of a cell, and that is based on what is the protein which constitutes the cellular structure over there. Okay. So now, typically in a microscope, if we look into it from a very engineering point, then what happens is that you have some white light which goes down. So if I look at the spectrum of white light, then it's supposed to be sort of uniform, but in general, it's not that uniform for any kind of a illumination system. So it becomes quite non-uniform, and white light will have some sort of variation in the range of wavelengths from 350 nanometers to 750 nanometers. And now you basically have on one side you are basically seeing what is the variation in wavelength, and then on the other axis what I'm seeing is what is the optical power. Now what happens over here is that for white light you are supposed to get down all wavelengths with equal probability or equal number of times all wavelengths should be present. So it's supposed to be a flat line, but then for a practical system it does not happen, and it has this kind of a bit of convex looking behavior over here which you see. Okay. So now from there this light goes, so this is the light which is coming from the bottom of the microscope or top of the, wherever the light source is, and this passes through the tissue over there which has some stains, and then what you end up getting is that given what is the nature of staining at a particular pixel, you will get on a different color. And now what you are going to do is look into what is the nature of the color at a given pixel, and since each color is associated with a different kind of a cell or tissue composition or say a protein, so you will be able to tell what is the things, what are the elemental things which make up the composition at that particular pixel over there. So that's essentially the whole point of microscopy or staining within microscopy, which is of use for us. So now in a microscope, this is what it typically looks like. So what you have is some sort of a lens tube which is present over here, and this is the one through which you see, and there is a light source present over here. Now, this light source is essentially from where the light comes up. It goes through this whole part, which is called as a condenser or an aperture point over there, and then you have the lens placed over here, which gets into. So the light goes through your slide, which is placed over here, into this lens, which is called as an objective, and this does a part of magnification. And in a simple case, you can assume that to be as simple as the lens which you use for reading. So there are these magnifying glasses which you use for reading newspapers or something over there. So those lenses are, if they are stacked one on top of the other, then that is what makes up the objective of the microscope through which you are going to look over here. Okay. So we'll come into it one by one. Okay. So now, in case of having a lens, what happens is that if you remember from your +2 level physics, then it is very simple. So the point is that you have an object or a specimen over here. It passes through. So if there is a light which is coming from. So in the earlier case, what you have is that there is a light which is passing through over here. Then in that case, this will be casting a shadow, and this casting of shadow will come down to your eyes. Now here that does not happen. So here there is some external light which is reflecting from here, and you have these rays being casted through your lens, and then it comes goes through your eyes and forms a image somewhere on the retina, and then that's the image plane which we are well aware of. So now if I look through this whole process over here, what you will see is that as I keep on moving this lens back and forth, so say now the lens is quite closer to this object over here, and then it comes even closer to the object, you would see that the closer the lens is to the object, the bigger is the size of the image which is over here. And the bigger the size of the image, now coming from that whole aspect of resolvability or resolution which we were speaking about, so the bigger is the size of the image, the easier it is essentially to discriminate between neighboring lines when they are placed very close apart. So you would say something like a higher magnification when you are able to discriminate between lines which are as such placed very close to each other. Are we clear with this part of understanding of resolution and the lens concept? People in the class, you can speak or you can at least type. Okay, good. So now a critical thing which you need to really observe is that see, in general, when you were studying about lenses in your +2, then your assumption was that you had something which is called as a thin lens. A thin lens model is it's as thin as just a paper. But then you know that you cannot make a lens out of a paper. A lens has to be bulgy in the middle, and it will be converging on the sides of it. So now that it is bulgy and then it converges, so this bulge is something which is going to take a significant factor. So now if this is my object, the closest you can bring this one is when the bulge touches this part over there. And so now if you look into this image on the rightmost side over there, so if this lens is pretty much thicker, and then I will come into why for a higher magnification you also need a thicker lens, and then it's very intuitive to understand, but a bit later on. So now this whole lens over here that is going to come closer and closer to this object over here. Now there is a limit to which it can come down. So essentially there will be a limit to what I can magnify at any given point of time. And this is going to pose a real problem, because after a point of time, I cannot really increase the resolution in any way, because, and then on the other side, you also see that if I want to have a higher resolution, I will have to have a thicker lens. If I have a thicker lens, then that is anyways pushing my lens away from the object. And if my lens is getting pushed away from the object, then my total magnification is also reducing, because the size of the image which is cast on the retina is reducing. Now this becomes a chicken and egg problem over here, that I want to magnify, but in order to magnify it, I will need a thicker lens. And if I have a thicker lens, then I'm not able to really magnify, because I'm pushing myself away from the object, and that in its own self is going to reduce the size of the image, and essentially it will also reduce the size, the total magnification which is happening. So this is a big problem which we have now. So what we do in a very standard case is we use something which is called as a compound lens structure within an objective. So what this has is that you have one lens, you cast a image of that lens, and now you put another lens somewhere over here, such that this image being cast from the first lens becomes the object for this second lens. So this becomes a virtual object for me now, and now that can also magnify. So now the problem which I otherwise had of a thicker lens can be solved by using a whole stack of lot of thin lenses, and one after the other, and very carefully placed such that when the image of one is cast, it is cast as the virtual object for the next lens, and that is cast as the virtual object for the next lens, and so on and so forth. Now, if you have some experiences of using real cameras, I mean a camera and not a cell phone camera. A cell phone camera does not have these kind of moving lens structures, and compound lenses is also not so popular. But today, like in most cameras which give you about 12 megapixel or something, which on a phone they tend to have, like if you have one like the phone which I have, which has multiple lenses over here. So there are essentially 3 lenses, and then there is a flashlight. So now this kind of a 3 lens structure, there is one lens which is called as a fisheye lens, which takes a wide angle one. There is another lens which goes into the depth over there, and the other one is essentially what is called as a coma sensor. Sorry, not a coma, a luma sensor. It senses only what is the total amount of light which is falling. Now, this is a compound arrangement which is done over there, but a similar kind of a thing for a microscope is what looks like this, and this is a thing which is called as an objective. Now, what is critical for an objective is one of these aspects, which is called as the total magnification factor of the objective. So here you see that this is 63x, which means that this can magnify anything which is below 8 by 63 times. Okay. So now in a standard microscope, what is present is something of this sort. So you have an objective over here. You would see that you have something called as a tube lens, and then there is a lens on the eyepiece. So generally this objective over here, say that being 63x, if you have a tube lens which is another 10x, and then you have an eyepiece which is again another 10x, so this means that you have 63 into 10 into 10. So that is 63,000 or 6,300 times of a magnification which you get down in total. Now, so you can essentially look into it. So if there are 2 lines which are at a separation of 1 micron is 10 to the power of minus 6 of a meter, then they will appear, by the time it comes into this eyepiece, they will have been stretched by 6,300 times. Okay, so now that means that a separation of 1 micron comes over here, or 1 micrometer comes over here in the eyepiece as 10 to the power of minus 6 into 6.3 into 10 to the power of minus 3, and that makes it 6.3 into 10 to the power of minus 3, which means 6.3 millimeters. So now anything which was just 1 micrometer apart, to your eyes it would appear as if now it is 6.3 millimeter apart. So that is the whole concept of magnification which comes to play. Now when we go over here to this lens, then you would see that this whole part is what is called as magnification. Next, you have this thing which is called as a focal correction. Now, this infinity, which is called as a focal correction, is what basically states that how far can it go, and any object which is very far off, how does it look like? So essentially, focused at infinity is a concept which we call. So if you remember from the pinhole camera, in pinhole camera, you know that any point in front of the pinhole is always in focus. It does not really have a focal limitation. So in case of a lens, there is a limitation over there. So now, in case of a lens, the limitation can be brought in something like this, that how does it cast all of these images over there? So to me, when I am looking at something, if all the lines of light are coming parallel to me, then however far or back I keep on going, I'm always going to perceive as the object is almost at infinity, or there is no distinction between them over here which is coming. So now here what you see is in focal correction, that if my beam which is coming as an output from here, so this part is the opening turret over there for the objective. This is what will go into my tube lens from here. So the light goes into tube lens. Now, if the ray is coming up as very parallel, then it becomes a parallel beam, and then what you get down over there is an image which appears as if it is coming from infinity. So that's the whole point. Now, what that would mean to me is that irrespective of how far or close the lens is, whatever is the magnification it does over here, that is the only final thing which is of importance, and nothing more. So if I move this one a bit up and down, there is not much of a change which will happen to my total engineering. But there are still a lot of careful things to do. This over here is a factor which is called as a optical aberration correction factor. Now, an optical aberration correction factor is something which helps you in understanding how much will be the spectral spread. Now, for spectral spread, I will get you back onto something of a lens. So now, let's look back into this diagram over here. You have this thick lens on your right hand side. Now, you can pretty much assume this thick lens to be made of two prisms. Okay, so I'm looking at just a 2D planar section of the lens. Now this is thick in the middle and this comes as thin in the sides and the periphery of this one. So now I can assume this to be two different triangles which are placed. So something like this. This whole structure is also going to be a lens for me. Say this structure. Now that this structure is a lens for me, this can be broken down into two different prisms. So this is a prism and this is a prism. Okay. Now whenever I have a prism and I have white light, a parallel beam of white light going through the prism, then you would see that that light essentially diffracts and you get down your visual pattern which comes out from the prism. So here also, as a result of this kind of an approximation of the lens as a prism, you will be getting a similar kind of a diffraction pattern. The only difference is that in case of a standard lens, it is going to be a flat one. In case of a standard prism, it's planar, but this line are no more planar, but this is a bit curvy over here, but that curve is negligible. I mean, you can pretty much assume that to be very close to a flat line. And what happens by making very realistic assumptions about that curve on the surface of a prism is that your light beam spread is going to even widen more and more. So now you know that if there is white light which is incident on a lens, you would on the other side see a rainbow pattern. So this is what will happen. And if you remember very carefully, or if you had tried this one down as a kid, or if you haven't, then you can try it out yourself these days as well, is if you try to focus a white light coming from very far off on the lens, then you would see at the periphery of wherever the focus is coming, there would be a bit of bulging nature. So it will not be a point light. So essentially, you know that if you have a parallel source coming down over there at your point of focus, with the magnifying glass, you will get down a point source, but it's never a point source. There is a finite width of that source itself. And you would also see that as you are moving closer and backward, the width does not pretty much change for a significant amount of movement of close and back and forth over here. And that happens because this light was diverging over there and there was a bolus which was getting formed, and this is where the visual pattern is getting created. So now that is of paramount importance for us. Now that whole thing needs to be corrected, and how that can be corrected is that you coat the lens with a certain kind of chemical which is not going to let that kind of a diffraction pattern set in. And so in fact, like glasses also have that. So the glass which I am wearing, this if like you can see some light reflecting over here on the lens. Now this light which is reflecting, that does have some sort of a color change which is coming up. And that's happening because there is a coating which is given on top of it, such that when you look at very far off things, it still appears as white. And that's one of the reasons why eyeglasses and eyewear are very costly, because there's a lot of engineering which goes in making these lenses such a way that you don't have different kind of magnification or different kind of a chromatic aberration for different light across the lens. So almost like I look at white paper over here versus I look at a white paper over here. Or I look at a white paper just in front of my face. It's supposed to be white, completely white, and not just have variations in terms of colors or appear as visual. So that's about the optical correction. Next comes down whether you are able to do a water immersion, and this is for the fact that sometimes you have a kind of a lab setup where you have a petri dish or a glass dish on which there are cells which are put on, and the lens has to go very close, so it will essentially end up dipping in water. So for that you need to have a sort of a ceiling over here such that no water goes in, because if water goes in, then what happens is there would be moisture deposition and there would be fungus growth inside over there, which will again create a lot of patchy artifacts on your lens. So now these are some engineering constructs associated with. Now this is something, an example which I have taken from the Microscopy tutorial web page. You can actually go and look into that web page for more details as well. So what it essentially shows is that if I want to increase my magnification factor, then there would be certain dependencies on a factor which is called as numerical aperture, which is essentially dependent on theta, or what is called as the focal angle, or the basically the lookup angle, or the angle of incidence of light over there. So if my lens is very close apart, then my focal angle is low. If it's very far apart, then my if my lens is very far away from my specimen, then this angle becomes very less. If my lens is very close to my specimen, or vice versa, that the specimen is very close to my lens, then this angle becomes higher. So this whole thing gives rise to a factor which is called as numerical aperture. And what a numerical aperture essentially indicates is what will be the total sort of difference between the farthest and the closest point which you have, and that is what is called as a depth of focus. So that depth of focus thing has to do something with the image resolution. So now for over here we have this example such that when you have a very low numerical aperture, then what happens? So a very low numerical aperture is associated with a very smaller theta, because it's essentially mu sine theta, and mu is 1 for us. So now that it's dependent on essentially sine theta, and then sine theta is a increasing, monotonically increasing function. If theta increases, your sine theta also increases, and it's limited. So at 90 degree it will be 1, and then again it will start decreasing. But maximum is 90 degree, because so this is the principal plane and this is the angle of lookup. So this can vary maximum and go till here. It cannot bend further. So it cannot be like it goes from here and then starts bending like this, because then the light is going to go the other way around. So that is not going to happen. So now here when your lens is very far off, then you would see that your numerical aperture is low, and as a result of that, the resolvability between these two samples becomes low and low. Okay. So this over here, what you see is what is called as an Heredis pattern. So that is the net result of the effect of what is created by a lens when there are a lot of points which are being seen through a lens over there. Now, the fact that you are not able to discriminate between them, so you are able to discriminate between this and this. So these are resolvable. Between this and this, that is resolvable. At this particular magnification, you can do that. But between this and this, it is not resolvable. Now, if I come down to the one on the right hand side, which has a higher numerical aperture, you would see that the resolvability has increased significantly. But then it also creates a problem which is called as aberration, that there are these kind of ringing patterns or ring-like patterns which are getting created around over there. So that's something you will just have to learn to live by, and really can't do around anything with that. So these are some cons of doing. So you gain something on the advantages, and then there are the downsides of it as well. So are we clear till here? If you can write and tell me, then we proceed to the next part of it. Are we clear till here, or you have some queries on this part? Okay. So let's go to the next part. The next is something which is of paramount importance, and this is what I was telling, is what is called as a focus depth. So now, if you look over here, what will happen is that because you had this kind of a airy disk or wavy-like pattern, so everything is cumulating together, and you will be able to see. Now, the other fact is that between two lines which can be resolved, you will see that it's never a point, but it's a distance which you can traverse. So essentially, what this means over here is that if your object plane is over here, then whatever is the difference between these 2 points which are being cast on the image, If you move this object plane till here or here, you will be able to see a similar kind of a difference. So which means that those sort of overlapping patterns which you see, if you move this object plane in this whole vertical range distance over there, there won't be any discrimination which you will be able to make. The only time it will be, or sort of like whatever is discriminable equally between this range to this range, and beyond this again becomes out of focus essentially. So now that distance is lesser for an objective of a higher magnification and is more for an objective of a lower magnification. Now there is an implication of this one which comes up. So what I said is I am slicing down tissues into much thinner layers. Okay. So now if I'm slicing down tissues into much thinner layers, now it's a layer. At the end of that layer does not mean that it's a zero dimension in the z axis. So if my plane is existing in xy axis, then it has zero dimension in the z axis. Z equal to like delta z, or the thickness around z is equal to 0. But for a physical system that is never so. So there is a difference between them. There is a thickness which you will be able to see. Now the point is that what I would want is that in whatever magnification I see, this depth, this thickness should be within the depth of focus over there. Now, if it is not within the depth of focus, then what will happen is I will have to move this lens up and down and change my focal points and then see it. So that is something like an autofocusing thing. You are seeing that in cameras when you take an image, and in fact, like when my webcam is doing it, you would see that typically my face, which is the primary object over here, stays in focus, but the bookshelf which is behind me, that becomes a bit hazy and it's not in focus. Now if I do an experiment, I bring my finger very close to the camera, you would be able to see that it does not focus on my finger. My finger is blurry when it comes closer and closer, but my face is essentially something which is in focus. Now when it comes somewhere over here or here, so this is where it becomes sharper, and then it keeps on going like this till a point over here that it will be sharp, and after that again it starts becoming blurry. So this is what is the impact which is happening because of this kind of a numerical aperture problem, and which creates a limited depth of focus. So this point from where you can see my finger in focus to this farthest point where it can be in focus is this whole double cone like structure which you see over here, and that is a depth of focus point. Now in case of a microscope, what that would lead to is that this was an example of an experiment which we had done. So we had 3 different threads over there, and now I am focusing on the middle thread which is red in color, but the moment I am able to focus and get most of the thread in red, I will not be able to see things which are in blue and which are in yellow. So now this should give you an example of what I mean by depth of focus and what is the challenge which is associated with that. So now what happens is that if your depth of focus is very low, then other things become out of focus. The only way you can do is that you bring your numerical aperture lower and lower. That will increase your depth of focus. Now everything is in focus, but then the discriminability between 2 neighboring lines gets reduced. So your resolution is falling. So there is this whole issue which comes over there. So in a modern practice of pathology, what you have is this kind of a thing which is called as a whole slide digitizer. So what it has is a cassette in which you can put down all these slides which you were seeing through a microscope. This is a microscope or robotic arm which moves and images. And now somebody says my video is stopped, but when I am transmitting from my side, okay. So now here what it shows is that on this kind of a monitor-like system, which is called as a whole slide viewer, you would be able to see all the slides and then you can magnify them and look into it. Now here comes the problem. So this is not the solution. The problem starts over here. So what you would see is that you can actually acquire these images in multiple magnifications. Okay. Now associated with magnification is something interesting which will happen. So if I am at a lower magnification, which is say 1x, then I am able to look at a much wider area. And as a result of that, because my size of the lens, so the whole say slide which I am going to acquire is fixed. So if this phone of mine is the slide which is now fixed. Now what will happen is at a lower magnification, I will have a bigger block size. So now the total number of blocks I will have to acquire one by one serially is much lesser in number than the total number of blocks I would have to acquire if the block size is small. And now the block size becomes small when your magnification increases. So now there is a trade-off. So I can either acquire everything at a lower magnification much faster and use less amount of memory to store this one, because it will be less number of pixels. I have to acquire less number of blocks. But then I'm going to lose out on the resolution. The downside is so that's my downside. Now on the other side, what I can do is that I increase my magnification and then I can start acquiring. So now my data will increase, but I will also have a higher resolution, and then that's pretty intuitive over there. That my data will increase because I have a higher resolution, so it's resolvable. But then look at the other side of it. The problem is that the moment you have a higher resolution, your numerical aperture decreases, and now that your numerical aperture decreases, you are now going to face a problem with respect to whether the whole object is going to be in focus or not. So if I am at higher magnification and this is my thickness of the slice, and I'm able to say whatever is, if I come closer. Now if the thickness of this nib of my pen is the best what I can do, now that it is going to be lower, so I will have to acquire more and more number of things on the depth axis as well. So now you see that this is a major problem which comes down in terms of leading the speed. Okay, so that's a problem which we were trying to solve in this particular case when this solution was getting developed. So this is the story about a work on computed super resolution microscopy, which we were doing in association with a startup company on digital pathology called as Signal. It's a Bangalore-based company, and I will show you a couple of more images on that. And this is from last year's ISB paper, which we had presented. So now what comes down is something of this sort. So the point was that given a low resolution microscopy image, so this is an image which was acquired at 10x objective magnification. The job which is at hand is you create a CNN which is going to create a high resolution image, which now we call as a super resolved image. And this is supposed to be equivalent to a high resolution image in real world, and that high resolution real world image is at 40x. Okay, so now here comes the whole point. So essentially I have a 10x sized image. I'm passing it through a CNN and I want to get an image which looks almost like it is at 40x. Now what I would gain by doing this is that if I was acquiring at actually 40x, then that would have created a lower depth of focus. So now I will have to acquire at more number of focal points over there. Now that creates a problem for me. So this is something which can get rid of that problem, because at a lower magnification I will always have the whole depth of focus curve. But then the problem is that the difference between 2 points is not that distinctly visible. Now you would come to me and ask a question that if it is not distinctly visible, then how do I get it in super resolution? And that's the learning trick over here. The point is that in general, when I say something goes down so from a high resolution to a low resolution, you can pretty much assume that to be something equivalent to an average pooling or a max pooling like operation. Now at the same kind of a problem which we had in max pooling, that you know what is the average value from all of those pixels which have come down. So if you are doing an unpooling, you would have replaced it by the same value in all the 4 pixels if you are doing a 2x2 max pooling kind of a thing. But then you don't exactly know whether that is what is coming, and there is no way in which you can get down the actual granular points from where these were coming. So this has to be taken care of, and somehow we need to solve this one. So here the point which comes down is that interestingly for microscopy things and for most of these images, there is a one-on-one mapping on what are those high frequency components or very resolvable components which relate to a certain group of low frequency or not so easily resolvable components. And because there is a relationship present over there, so we can actually have a learning model in order to have this 1:1 mapping being learned and then replicated. So now in order to do that, we start initially with doing something which is as simple as a reconstruction loss. So this is a simple mean square error. How the mean square error is calculated is you calculate the mean square error between your super resolved image and the real image, and you know that this again looks very similar to a convolutional autoencoder itself. In fact, like I remember we had used a UNet over here to do it, and then eventually we modified the model, and now we have some more improvised models in order to do that. But then this does not solve all of your problems. So what happens is that Typically, if you look into this whole image of what we have over here is called as a blood smear. So a blood smear consists of a slide in which you smear up the blood and then you look into the different cells present in a blood. Now what you have in a blood is basically plasma, which is that fluid part. Then you have RBCs, red blood corpuscles, and then you have WBCs or white blood cells, and WBCs have different types of WBCs which are present over there. So now these WBCs have a lot of granular structures and which are of high resolution, and you want to really discriminate between them. But the RBCs are not anything of that sort. So now here that I'm trying to do that, what will happen is that majority of the part is WBC, majority of the part is RBC and or is a white background which is flat. So even if I resolve it out, because there is not much of a granular details which has to be really discriminated, so I will not be able to see any discrimination which comes down over there. And now as a result of that, my mean square error is going to be very low. So now I start training the network. Even if I do a interpolation, something like a bilinear interpolation or a bicubic interpolation, I would already get a very low error over here, and that is guided by majority of the constitution. Whereas the challenge is essentially to get a super resolution happening on these components, which are the WBCs, which have a granular nature and are of a high frequency nature over here. So that becomes our challenge of all sort. And that's what we are trying to solve over here. So for doing that, the problem is that how can you do it? So can we have something like a very specific loss function for this? You can say that I can mask it out and only in this area let us calculate the mean square error. But then we found out that mean square error is not always a very good way of doing that, because what will happen is if you have jittery like structures, then the mean square error between that and there is a DC shift or just an intensity shift between those becomes the same. So you don't really know that whether I'm able to reconstruct these kind of jittery structures or am I just pushing the intensity level by a different level. So this whole issue still stays over there. So for that, we started looking into using a Turing test loss, which I was discussing the earlier. So now in this case, what you do with the Turing test loss is you have one Turing test loss in which you compare between the super resolved image and the real image in a Turing test format. So this is just a relativistic Turing test. You put both the images together and then ask it to predict whether the first channel is real and the second is super resolved or vice versa. So this was that standard Turing test function which we had studied till the last one, and the last lecture which had an example from ultrasound simulation. Also, you have seen how that Turing test really works out. But then here also the problem is that this Turing test does not get itself very much good in performance, because majority of the constitutions over here are still of either the white background, which is made up of because of the plasma constitution, or the RBCs, which are very flat in nature, and there are only few WBCs, and then it's not able to really emphasize on the WBCs over here. So now what we do is we get down another Turing test, and this is where we brought down an interesting engineering. So here what we said is that let's focus only on the WBCs. So now in order to get the WBCs, you would need some sort of a region proposal coming over here. So region proposal is essentially that which region consists of my WBCs. Let me run a Turing test only on those regions, and then I will update my model accordingly. So now you can run a Turing test on a region proposal based thing, but for this one way is like you have manually drawn masks over there, or otherwise you can run some sort of an object detector. So we'll come eventually to another lecture where we will study about object detectors as well. So if you are running an object detector over here, then that object detector can get you these things. So that can be a separate neural network which you have trained only for detecting where WBCs are present over there, and that is going to help you. So now you can look at that systems when they get built, it's no more just one single neural network. So by now you have seen that in order to get a Turing test, you will need another neural network along with that. Here that we have two Turing tests, you need in total there are 3 neural networks. Now if my region proposal is also another neural network, then you see that in an engineered system over here, you will get down 4 neural networks. So it's no more a case where you are just learning with one neural network itself, and then they work hand in hand. Okay. Now here that I have this second Turing test coming into here. So this helps me in really improving how the appearance of these WBCs get treated. And finally is when you do the adversarial transformation through the CNN, and then you weigh down the losses of both of these Turing tests in a way such that the CNN can do an adversarial attack on the 2 Turing tests over here. So that's what we want to achieve. Now because the two Turing tests have a different size of an image, so that will lead to a different size or the different magnitude of the loss function over there. So you need to basically balance their magnitudes, and that's by using these two coefficients alpha and beta. And alpha and beta are essentially my sort of balancing coefficients for different kind of Turing losses. Okay. So now once this is done, then this looks at the final model of what is used for training and then getting the super resolution working over here. So I just wait and I would ask you if this is clear till here for you guys. Can you just respond? So Raghavendra, you will have to look through the Turing test, which is from 2 classes earlier. So please, the lectures are uploaded. If you had not attended that class, then you can have a look at that. Okay. So now let's proceed from here. So now, as a result of this, this is something which we are able to get. So now what you would see is that there is a real image, and this is of actually the WBC at 40x. Now this is what is called as a bicubic interpolated image. You can yourself read about bicubic interpolation. It's just a different method of interpolation using a cubic polynomial working in two different directions along the x-axis and y-axis. That's why it gets down that name called as bicubic. Now in bicubic interpolation, if you are using it, then so this basically takes a 10x image and then interpolates it to 40x. So that's a 4 times interpolation which you do with the bicubic method. And now if you do that, then this is what it starts looking like, which is not going to give you so much of a detailing in terms of the what you would be getting down in a real image of the WBC. Now, if you use a standard super resolution network, this is basically train the network with just mean square error loss and maybe a standard GAN-like discriminator over there. You are still not able to get it because what will happen is it gives you a very good performance around the RBCs. You can see how intact they are, but then in the WBC it really loses out. So now when you bring in Turing test, you would see that this details start popping up over here. Now similarly, the top row is basically where you look into blood smears or WBCs over here. The bottom row is when you look into lymph node biopsies, and then this is a different organ. So essentially, because it's a different organ and a different set of image from a different microscope, so your alpha beta values during training are also very different over here. So now here you would see that if you are doing some sort of a bicubic interpolation, then that comes to you almost as if this has been wiped off or somebody has done a water painting, or there was a painting done and then you spilled water on top of it. So everything becomes hazy. Now this is what is essentially something which you can associate with loss of resolution. Now if you go down to a super resolution one, you would see it does not really help you in restoring those granular details which you had in the real one. But then if you go towards this T1 and T2, they are basically using this one Turing test or both the Turing tests. You would see that the details really start popping up over there, and that's of immense importance. Now that these details have started popping up, this is something which is going to be of real use for us. Okay, so what we could gain with that? So here what you see is this is the machine which is called as AI100, and then this machine is the microscope on which this whole AI engine sits over there. So this is a digital microscope, and we did not build the whole machine. We just built the super resolution engine over here. So what you can do is that if you are acquiring at 40x, it takes you about 30 minutes in order to digitize this slide. But if you are acquiring at 10x, then it will be basically 1/4 of the time reduction, because every patch becomes 1/4 larger area covering in size. So now instead of something which used to take 30 minutes, now it's going to take in the order of just about 8 to 8.5 minutes of time. So now under 9 minutes, you can pretty much use it. Now that you are able to acquire things under 9 minutes, this basically speeds it up. So earlier, whatever would be the total number of slides you can acquire or you can image, now you can image 4 times more number of slides by doing this. Now here you would see that what it shows is what is the scale factor or what is the resolution factor over there, how much of super resolution factor we have done. So if I have acquired some image at 10x and I am scaling it up to 40x, then that is a 4x of a scale factor. Now 9x of a scale factor means I have acquired at 10x and I have scaled it to 90x, or we do the vice versa. So what we have done is that 40 by 9. So the uppercase we were always trying to keep it at 40x, and the lower one can be any lower magnification from where we want to reach our target of 40x. Now what we see is that you have different kind of scaling mechanisms. You can have nearest neighbor interpolation, bicubic interpolation, and these super resolution methods, including our Turing test loss based methods, which can be just one Turing test or two Turing tests. Now here that you have this one, what we do is there is an AI engine which this company had developed in order to find out all the WBCs. So SIGTuple has its own AI engine to find out WBCs and then count what are the total number of WBCs, or where certain WBC has been identified into a typical class of a WBC. So WBCs can be neutrophils, basophils, eosinophils, and so on and so forth, 13, 14 types of them. So now what we do is, if you actually image that slide at 40x and you acquire and you found out that these many are over here and these locations have these as classified. Now if I scale up from 10x to 40x and give you this image to the AI engine and then ask it to find it out, then what is the performance, or what is the total concurrence between these two findings? So this was just to look at how much is the impact of this super resolution in terms of a drift in performance of the actual object which I am imaging over there. Now here we realize that because of changing over here, there is not much of a change which comes down, because essentially you have almost a 98 to 99% of a concurrence which comes down over here, and that is really interesting. So if you are sometime around Bangalore or after the lockdown gets over, so you can actually go to this company called as Human Diagnostics, and they run this engine over there. So SIGTuple is what manufactures it. It's just a couple of blocks away from it on the same road. It's on HSR layout, so you can just Google it up and find out where the location is. And then it would be interesting to go and see a blood test getting done in pretty much real time. So that's what I had to say about one of these applications on super resolution microscopy. So on the take home message, I would suggest you to once again revise on details from the tutorial on variational autoencoders by Carl, and you can also get into learning more about adversarial autoencoders from this archive paper from Goodfellows group. So that's all we have for today, and thank you.